All right, we are in Pset 8 solution videos. So we're looking at this problem here. Booming industry, looking at underwater luxury homes, looking at piping materials, So we're thinking of using CO. We have to put this, so basically we have a system like this. Our cell, our cobalt. So we're looking at cobalt, metals in contact so it won't corrode. So I'm going to go ahead, because we know if electrons flow from the negative to positive terminal, that is going to be a positive voltage. So if we flow from positive to negative, there'll be negative voltage. So I'm going to actually put cobalt on my positive side as my positive electrode, positive terminal, actually positive electrode is fine. And then I'm going to look at all these other ones as the negative. So we're going to look at if CO, the standard conditions minus whatever this side is, if that's negative, that is going to tell us that our cobalt will indeed corrode. Blah, blah, blah. So first we're going to look with standard conditions, and then we'll see basically where they're going to flow. So we're going to actually pull up our Canvas site. We're going to go to our, let's go ahead and we can just go directly into our lectures. Let's go into, not polymers, but let's look at corrosion. Let's see. Let's go ahead and download this. All right, so let's go ahead. So this is our standard conditions. So we are going to look at what are the systems. Let's do side by side for now, because we are going to look at AU, PT, CU. All right, we've got quite a AU. So AU is equal to, AU is going to be 1.42. PT is going to be equal to 1.2. CU is going to be equal to 0.34. We know that we're looking with cobalt, which is going to be minus 0.277. What else do we have here? AU, PT, CU, and then MG. So we've got quite a few. All right, let's try to MG, ZN. Here we go. MG is equal to minus 2.363. Cn is going to be equal to minus 0.763. We have Fe is equal to minus 0.44. And Cd is equal to minus 0.403. Sn is going to be equal to minus 0.136. And then finally, Pb is going to be equal to minus 0.126. So, that's a lot. So I'm going to call this list equals AU, PT, CU, CO, MG, Cn, Fe, Cd, Sn. And I'm going to remove cobalt because that's the one we're looking at here. So this is our list. So I'm going to take CO minus list 1. So this is negative. So that means that electrons are actually flowing from the positive terminal to the negative terminal. So any negative value here is going to be where cobalt is corroding, which is not ideally what we want to have. So the electrons, and we know where the electrons are flowing as well. So I from 1 to length of my list. Here we go. So corrode, corrode, corrode. Don't corrode, don't corrode, don't corrode, don't corrode. And then finally corrode. And that makes sense looking at kind of the table that we have here. Everything above cobalt is going to be more basically noble and more cathodic. So it will corrode for anything above here. Below is going to basically, it will not corrode. So our standard temperature and pressure conditions are going to be 1 atm pressure, 298 Kelvin, and then we're in a 1 molar solution of each of our cathodes and anodes. So boom, boom, boom. Calculate the temperatures where you can switch which material corrodes if we're working with an anode solution of this and a cathode solution of this in its own ions. All right, so let's go ahead and let's attack this. So let's say, usually an anode and cathode. If I were to, for example, and this is kind of the true, let's say cobalt, and we'll actually bring this here. Let's say we're looking with, let's say cobalt in, let's say over here, this is magnesium. So we know that cobalt on this side, cobalt will be going from cobalt 2 plus 2e minus to cobalt because it's reducing. It's going to gain electrons. We know that Mg, on the other hand, is going to go from Mg to Mg2 plus 2e minus. So the full cell reaction will be CO2 plus Mg goes to CO plus Mg2 plus. So we're going to be looking at the concentration of products, which will just be Mg2 plus, which is our anode, over our cathode material, so we CO2 plus. So basically, in our Nernst equation, we're going to be looking at E, and we're trying to figure out when it switches. So we're trying to see, really, we already calculated our E naught previously. So we calculated that E naught in the previous setup of this problem. So we need to see when is this equal to 0 minus, I think it's, and then actually let's go ahead and look at our Nernst equation. So let's go back, let's look at our lecture 7 notes here just real quickly. It's nRT because we need to define some values. So we're going to be using our Nernst equation. E minus E naught nRT, minus RT over NF. Okay. So let's go ahead and define our F is equal to 96485. That's our Faraday's constant. Our capital R will be equal to 8.314 joules per mole K. So what we need to do, and let's go back to our equation here. So minus, let's go ahead, minus RT over NF, natural log of our concentration of the anode over cathode. So we can go ahead and we can put that value is set. So the anode 0.15 over 0.85. So we need to see now, so solve, when does 0 minus, and we're going to call this my E naught L. So minus E naught L 1. Let's set this equal to minus R times T divided by, and we're going to make an assumption that the number of moles transferred is going to be 2 each time because it's cobalt. F times natural log 0.15 divided by, actually 0.85. Actually, no, 0.15 divided by 0.85. So we can find the temperature, and we can repeat that, and we're going to do this over and over and over. Make it a little list. Check it twice, even though Christmas is over, or holiday season is over. And you can find those temperatures to basically flip which material is corroding and not corroding. There you go. Awesome. All right. Look at the experiment below. For each cell, indicate where electrons are moving, what material is electroplating. So the material that's electroplating is the one that's not corroding. So we're going to say, looking at this, again, if it's a positive voltage, electrons are flowing from here to here. So here to here, electrons are flowing. If not, they're flowing from here to here, here to here, here to here. So the material that is gaining electrons, that's electroplating. Electroplate, 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 electroplate. Rank the relative electronegativities of the anode materials. So we know here, any positive one is giving up electrons. So Y is the worst, lowest electronegativity. Then, in this particular example, platinum, for these conditions. And then the most negative is gaining. So the highest would be X. The next would be Mg. And then right here, this would be Z. There you go. So I want to create a sacrificial anode to protect CO when connected to CU. So we have a system where we have CO and CU. And let's look at our system here. Let's look at our, so we have CO and it's connected to CU. So we know that CO is going to die. So what is the question asking us? CO is going to corrode. Where's our, oh shoot, let me go back to our, all right. Draw one composite configuration, identify the sacrificial anode, create another sacrificial to protect CO even better. So basically, we need to put some material in here that will work. So to protect CO, we can pick any material that has an electronegativity less than cobalt. So let's go back to it. So we could pick any material below CO here. And so we can pick CD, Fe, Cr. The best, the most, basically the one that's the least here on this table would be potassium, K. So there we go. And that is it. That is Pset 8 solution. So we will see you next time. Thanks. Bye.